Our second example again involves a horizontal object, but there is a force acting on that object, actually two forces that are at angles, and so that adds a little more complexity to our work. We are asked to find the tension in the wire on the bar. There's a misprint in the question there. And then also the force that the hinge exerts. The hinge is going to be supporting the bar from the left side and the wire from the right-hand side. So let's take a look at these forces and how to draw those on the bar itself. So there would be a tension force that is right along the same direction as the wire pulling on the bar. The weight of the bar itself, 16 newtons, should be imagined right at the center of the bar, so halfway in between. And then this unknown force, I don't know the exact size or the angle, and so I'll just make a guess about the direction. I do expect it to be upward because I need to have something on the left side to sort of cause the bar to want to rotate in the clockwise direction. And also I can see that there is a component of tension that pulls to the left, and so I expect that I need a component of some sort of force pulling to the right. So that is my guess. If I choose that direction incorrectly, I'll end up with negative values of my components for F, and so that'll just be my hint that I've chosen the wrong direction. One of the things that we'll need to do is, again, to break these forces into components, because we want to think about the system in the x direction and in the y direction. That's our reference axes. So let's go ahead and start with the tension force. I would need to separate that into a left and an up component, and I'm going to need to know an angle. I've labeled that angle phi, and another symbol we can use for angle to keep it straight from my theta on the left-hand side. And just using a little bit of trig, we find that phi is going to be 36.9 degrees. I'm also going to have to think ahead about the components for this unknown force F, because I am interested in what's happening horizontally and vertically. So I'll go ahead and put some components in there. I could certainly just call those components right away, F cosine theta, F sine of theta, but I find a lot of times it's easier just to call them components first, and then we'll build a triangle at the end to find out what the overall size of F is and the angle. So let's begin by looking at our forces in the x direction. So you can see that there's just an FH and then a component of T. And so we can write the statement that F of H must equal T times the cosine of that 36.9 degree angle we determined before. And then in the y direction, the forces that point up have to equal the downward forces. And so we have this F sub V, the vertical force, and we have the other component of tension. Those both point upward, and then they together would need to equal the 16 newtons that are pulling down on the bar. Now, neither one of these equations really gets me where I need to go right from the start, but I'll come back to them later when I try to answer part B of the problem. The most important equation really is the tension equation, the one that involves the torque equation. And so in this case, I have done a few things. So let's break down this work that I just popped up here. The torque values need to balance, and so I am considering the hinge to be the hypothetical point, even though it's not actually rotating. I'm imagining what would happen if it tried to. If there was only tension and not weight, the hinge would rotate in the counterclockwise direction. And if there was only weight and no tension, then the object would rotate in the clockwise direction. So I know that those two torques must be equal because it's not actually rotating. And again, it's the torques that are equal, not the forces that I'm looking at here. Now, we certainly could find what the length of the bar is. It's really just a 3, 4, 5 triangle, but I want to show you what happens if you don't know that distance. So I'm just going to call the length of the bar L, and that means that that 16 Newton force is halfway across, so L over 2 would be the value for the R, the radius. And then 16 newtons. And then to finish off the torque on the left-hand side of the equation, the sign of 90 again is just 1, so I don't need to include that. But here on the other side of the equation, I do need to include an angle. The tension force, because it pulls at an angle of 36.9 degrees to the bar, I need to include that in my work. And a reminder again that the sine component, it represents the perpendicular component of tension. So we're really just saying only use the part of this tension force that can do any sort of a job in rotating the bar. The other part, the cosine, it points directly along the bar, and you can't make something rotate with that direction of a force. So we set these two things equal, and we determine a value for tension. The L's just cancel out, so again, we didn't really need an exact value for the length. And we get 13.3 newtons. To handle part B, I want to figure out first what that F sub h and F sub v components are, and so we'll plug those back into our equations from the forces, and we find 10.6 and 8 newtons. And then I'll just take those and build a triangle so that I can see how they combine together to create the resultant force, or the force F. Now it turns out in this case that we sort of get back to where we started. The force F actually has the same size and sort of the mirror image direction of the tension force. And that kind of makes sense because this is sort of a simple looking diagram in terms of the symmetry. And so it would make sense that the two sides would look very similar. But the process is what led us to this point. Other problems can add an extra mass in there, which will sort of ruin that symmetry. Right, the next video then takes on what happens when the bar itself is at an angle, in addition to having some angled strings.